All right, so I'm just gonna do this one problem, and Roberts, considering you had the other review session with Dr. Denard. So this one's just kind of a long problem, but it goes over like most everything with series and parallel, CSTR and PFR, so it's a nice problem. So basically it gives you this these reactions. Ethylene glycol is manufactured by hydrolysis of ethylene oxide. And however, ethylene glycol, the desired product, can react with ethylene oxide to give diethylene glycol. And so then you just present these as A plus B goes to R, and then A plus R goes to S. And then it gives you the rates. So, zoom in. So we have okay, so we have our disappearance of B is just elementary reaction rate, and then the production of S, also elementary. So the first question just asks, classify this network of reactions. So for part one, so you can see that we have parallel reactions because we have A can either with B added can go to R, or with R added can go to S. But we also have a series of reactions where B with A added goes to R, and R with A added goes to S. So this is a mixed series parallel. And so I hope that's pretty straightforward. So for part two though, it's gonna say we have a CSTR, and the concentrations in the feed of CA naught equals 5 moles per liter, and CB naught equals 40 moles per liter. And it says there's no R or S in the feed, so CR naught equals CS naught equals 0. And then the concentrations of B and R in the effluent stream of the CSTR are 38 and 1.9. So our CB equals 38, and CR equals 1.9. These are both mole per liter. And then it asks, what the value of K2 divided by 1, or K1 is. So the first place you want to start for this problem is you want to do like the simplest, do the balance on the simplest, I guess, constituent. So A, we have parallel for A, and R we have series, but B is only in this first reaction. So B is going to be the simplest balance. So for B, we can just write our design equation for CSTR is just going to be volume over FB0 equals X over by disappearance of B. So then we can since we are given CB and CB naught, it's going to be easy. Say given. So normally we would use this to calculate X, but we're given CB and CB naught, so we actually know the extent of reaction. So we want to convert this just to be in terms of the concentrations. So this is going to equal B over FB naught equals CB naught minus CB divided by CB naught. And so that's just the value of conversion. And then the rate is just the disappearance is CA times CB. And so then we can further simplify this. We can change this to be, we can bring the CB naught to the other side, multiply it. So we have B CB naught flow rate, molar flow rate of B, and CB naught minus CB, K, CA, B. And then this is going to be, so we can substitute these two for our volumetric flow rate. And so then this is going to be equal to our tau, our time constant. And so then we'll get K1 tau equals CB naught minus CB over CA CB. All right, so that's the most simplified expression for the balance on V.
So wait, what was the substitution that you made?
Okay, so yeah, for tau is just this CB naught over FB naught, that equals your volumetric flow rate, and then V volume over your volumetric flow rate equals tau, your time constant. Does that make sense? And then I just moved the K1 over to this side. So then we can move on to our balance on R. And so for this one, we have N minus out plus Gen, this accumulation 0. So we don't have any input of R. And so then we're just, and then our out is going to be, so this will be V naught CR. So then the minus, and then plus our volume times our generation of R, and then minus this, oh yeah, and then minus the consumption. So the second rate equation, which is, yeah, K2 CA CR equals 0. So then we just want to simplify this. So we have plus V, we can do K1 times CA CB minus K2 K1 CA CR equals 0. And so then we can just divide. So now we can see that if we have this, if we just divide by V naught, then we'll have negative CR plus V over V naught K1 CA K2 K1 CA CR equals 0. Okay, so now what we can see is that we have this is going to be equal to our tau, and then this is what we want to find in the problem. So actually, we also have, so this is going to be simplified then to negative CR plus tau K1 CA CB plus K2 K1 CA CR equals 0. And so this tau K1 we have calculated a value for from the balance on V. So we can plug that in. So then, and we can move the CR over to the other side. So just say this equals CB0 minus CB for CA CB times CA, CB, plus K2, K1, CA, CR equals 0. And then we can multiply this through. So this will just equal 1. This will be minus K2 or K1, and then CR over CB. And then we actually have, and if we look back at the problem, we have, so we have our variables are CR, CB, CB naught, CB, yeah, and that's it. And we're given CR, CB, and CB naught. So we can actually calculate then this value of K2 over K1. And so we plug in those numbers, and we'll get K2 over K1 equals 1 from plugging those in. So yeah, the hard part of that one is just knowing where to start with the balances. So I always start with like the easiest one. So in that case, CB. So for the next part, it asks the volumetric flow rate to the CSTR is 1 liter per second. For same inlet and outlet concentrations, what is the volume of the CSTR? Okay, so now we need to calculate basically, so it's given us V naught equals 1 liter per second, and we need to find V. So we basically need to find our time constant tau, which we already have an expression for. So we look up at our, back here, we already have a expression for our tau, so we can do that. So we have K1 tau equals CB naught minus CB over CA, CB. And so it says all the concentrations are the same. So we already have CB naught, CB, CB. The only thing we don't have is CA. So we need to find that. So now, how are we going to find CA? We have CA naught, which equals 5 moles per liter. So basically, we can make a stoichiometric table. So we have in, out, in our A, B, oh, not C, R, and S. So we have CA 0 equals 5. We have CB 0 equals 40. CR 0, CS 0 equals 0. And then our out, we're going to do this in terms of extent. So our first equation is A plus B goes to R, then A plus R goes to F. So this is, say, equation 1, equation 2. So our extents. So the concentration out of A is going to be our CA naught minus extent 1 minus extent 2. Our CB out is going to be CB naught minus extent 1. And then our CR out is going to be equal to our extent 1 and then minus extent 2. And then S out will be equal to extent 2. So our CA is what we need to find. CB, we have this equals 38. And then we're also given CR, so this equals 1.9. So using this, we have two equations and two unknowns. So our extent 1 is going to, because CB naught is 40, it's just going to equal 2. And then that means our extent 2 from this equation, the equation for R, will just be equal to 0.1. So now we can calculate CA is just 5 minus 2 minus 0.1. So this will be 2.9. Oops, sorry. That a little smaller. All right. So now I can just plug this in. So we have, again, our K1 equals, this K1 equal 1 times 10 to the negative 6 liter per mole second. Okay. So now we have K1 times our volume over our volumetric flow rate equals CB naught is 40 minus CB is 38, and then divided by CA, which is 2.9 times CB, which is 38. So plug this in. So I can just plug in these values. So this is 1 liter per second, and then times 1 times 10 to the negative 6 liter per mole second. And so then volume will equal 18,148 liters. All right, so the next problem, or the next part of the problem is going to be, given that it says if K2 over K1 equals 2, what is the concentration of R in the effluent from an isothermal PFR that has the same feed as the CSGR above and has the concentration at B in the effluent as 38? So in this case, K2 over K1 equals 2 instead of 1, what we calculated before. And then our CB is the same as 38, but it's a PFR, and our inlet concentrations are the same. Okay, so now I'm switching to PFR. So K2, K1 is 2. Find CR, and then our CA0 equals 5. CB0 equals 40. CB equals 38. All right, so again, we're going to start with balance on B because that's the easiest. And so this is just going to be basically the derivative of what we had before. So easier. partial derivative volume over FB0 equals partial derivative XB over the disappearance. And so again, we'll just convert this to instead of XB, since we're given basically the XB will just convert to concentrations. So this will be negative dCB over CD0 divided by the rate, which is K1 CA CB. And so this comes from just converting XB. So if you take the derivative, it'll be negative because you're losing. As extent goes, you're losing. The concentration's going down as extent goes up, so that's why it's negative. And then, yeah, we'll divide by CB0. So this is going to be, so if we divide, so dV, or we multiply by CB0, and FB0. So this will be so we can just do this. So we can just say, since volumetric polarity is constant, so this just equals tau. So then we're going to have, by simplifying this, we'll have dCB. We'll move this tau, divide by tau, and then multiply. So we're just moving, sorry, I keep writing with my hand but not drawing. So we're just moving this equation around to simplify it. Hopefully you can see. And then this will be equal to K1 CA CB. Or negative, sorry. All right, so that's our equation, design equation for the balance on B. So next we do the same as before, we do it on R. So in this case, so we'll have N out gen plus gen equals accumulation. So our N is just going to be volumetric flow rate times CR. Our out is going to be volumetric flow rate times CR plus the derivative of CR, so it's delta CR. And
How
then
come for B you started with the design equation, but for R you start with the in minus out?
Yeah, you can start from, yeah, I mean you can start from N minus out for this too. It's the same thing. So N would be V times CB0, and then out would be V CB, and then plus the generation, or actually, sorry, this is and then, sorry, yeah, you can definitely start for, like, to be totally complete, you can start from so this is V naught times CB naught minus V naught CB plus the volume times K1 CA CB. I think, yeah. actually, yeah, balance on, so it should be minus, I think. Yeah, so it's the same thing. This is just simplified. So you can do the math and simplify it to that, right? It's just, yeah, if it's just a simple one like that, we've done it. So generally you don't have to like write it out each time if you don't want to. But it's always good practice to know like where it comes from and do the material balances, obviously.
I guess then how come we don't just start with the design equation for R then?
Yeah, so the thing, so it's, I mean, you can, I guess. I think the reason I'm not doing it is because we're gonna want to get like this tau. So yeah, I mean, you definitely can. I don't know why I did it this way. Yeah, you can do it. You can do it both ways. Yeah, sorry. I tend to do it with like the more complicated ones. So then this is plus K1 CA CB, and then minus K2 CA CR. Differential volume equals 0. So then, oh, sorry. So we can divide by the volumetric flow rate, and that'll give us CR. Sorry. So these are gonna, so these two are gonna cancel. So then we'll be left with VCR. We'll divide by volumetric flow rate. It's going to equal VB over V naught times. So we'll just make this tau. And then that would be K1 CA CB minus K2 CA CR. Yeah, so you'll be left with the same design equation. So if you just plugged it in the design equation. Yeah, we can compare. So our design equation for the PFR would be dx over negative r, and then it would be dv. So yeah, I mean, you could plug in the concentrations. I think this is why I started, is just because so you don't have to basically do the substitution. You can just do it in concentrations from the beginning. So you'd have to just, do the switch that into concentrations. So that'd be CR minus CR naught over CR, I think. But yeah, it's fine either way. All right, so I'll just erase that. Okay. So then we now have so now we have both an equation for partial derivative of CB with respect to partial derivative of tau and partial derivative of concentration R with respect to tau. So we can divide those two equations. So we'll do CR dCB, and this is going to be equal to K1 CA CB minus K2 CA CR divided by negative K1 CA CB. So then this will simplify to so this is just going to be -1 plus K2 over K1 CR over CB. And so now we'll just move this. So now we want to get this in the form. This is where we have to do the integration factor to solve this. So the integration factor will be, so if we have dy dx plus p plus p is a function of x times y equals q. It can be a function of x. Yeah. So then our integration factor is going to be equal to e raised to this p of x dx. So in this case, we have dCr dCB minus K2 or K1 CR over CB equals -1. So our Q equals -1, and our P of X equals, sorry, this P of X equals -1, and our P of X equals negative KT over K1 1 over CB. Or we're going to say, I'll just simplify this to say K2 over K1. Oops, sorry, K1 equals big K. And then we'll just say P of X equals negative big K CB to the -1. All right, so then our I is going to equal e to the integral of K CB to -1 CB. And so this is going to be equal to e raised to the ln, the natural log of so it'll be -k ln of CB, which will equal e to the CB -k. All right, so now we need to multiply our equation by this integrating factor. So we'll get, oh, sorry, this is, so this is e raised to the ln. So then that equals CB -k, sorry. All right, so then we can multiply our equation by this. So we have times CB to the -k, and then minus K CR over CB times CB to -k equals negative CB omega K. All right, so now we can integrate this and integrate this. So the reason we can integrate this is because it just ends up being the product rule. This is CB of CR times CB omega K. And so then this is just going to equal and out of CR CB omega K. And then integrating this side, we're going to get negative sign CB negative K plus 1 divided by negative K plus 1 using the power rule. And so then for, so the n on each side is going to be, so it means CR0, CB0, and CB, CR, CR0. Well, in this case, no CR, so just CB0 and CB. All right, so can do CR times CB K minus CR0 CB0 K, and this is going to equal 0, so this term just goes away, and that then equals can do, so we'll just apply, so I'm just going to move this in there to be K minus 1, and then we can multiply that by our CB of K plus 1 minus CB0 negative K plus 1. And then we have everything we need because we're trying to find CR, or sorry, trying to find CR. CB equals 38, CB naught equals 40, and this big K equals 2. So if we plug those into this equation, solve for CR, we get CR equals 1.9 moles per liter. All right, so, and that's the last part of the problem. So I hope you guys were able to follow that. I'll upload this video and this PDF. Yeah, if you guys have any other questions, just you can ask them now, or
yeah, I joined late, so like,
email
what
me
was
later.
this problem?
Oh yeah, so I'll post this whole thing. The problem's at the start. It's actually 716 in the book.
Okay.
But I just did it because it goes over like it's like a mixed series parallel reaction, and then
Okay.
it has like a part with the CSTR and a part with the PFR. So it pretty much covered
Gotcha.
like all the bases. And so I guess the only thing I didn't cover was like selectivity, but I know Dr. Denard went over that in his review session yesterday. So yeah, you guys can just look at that. Yeah.
So with I think it's with parallel reactions or multiple reactions.
Yeah.
He wants us to use extend a reaction in solving them. I think that's what he said.
Yeah. Yeah, you have
Because
to.
it gets complicated with conversion.
Yeah, because the conversion will be, yeah, because if you have like, what's done here? Yeah, because if you're like, if you have like A goes to R, and then maybe you have like S goes to A, and A goes to C or something like that.
Mhm.
I mean, you have 3 reactions with A,
Yeah.
right? So like you're not going to be able to just showing, you know, you can count your CA. So you normally calculate conversion as like CA naught minus CA over CA naught, right? But this is actually taking into account like all these 3 reactions. So you can't, you know, the extent's going to be wrong.
Yeah. No,
Or I mean, the
conversion,
conversion
yeah.
is going to be, the conversion will be wrong, right?
Gotcha.
This is like minus E1 plus E2 minus E3. So if you try to just lump these all together, yeah, it doesn't work. Any other questions? All right, well, I'll stop recording and then, yeah, if you guys have any other questions before the exam, I'll try to get back to you, but I can't guarantee it because I don't have like great internet service all the time, but yeah, hopefully